Okay, continuing this module. In the second part, we're going to kind of concentrate more on how matrix algebra applies to this course. So square matrices, they're the basic matrices we're going to deal with. So the main diagonal of a square matrix is the diagonal that goes from top left to the lower right. So the ones that are like AII. The identity matrix I has ones all down its main diagonal and zero elsewhere. And it is an identity, it's the multiplicative identity. And so, for example, there I've shown you an example of a matrix times the two-dimensional identity matrix, and you see that that AI actually equals A in that situation there. Now, there's two important functions on square matrices that we deal with. The first is the trace, and that's the sum of the elements on its main diagonal. So, for example, the trace of that matrix 2, 1, minus 3, 4, the main diagonal is 2, 4, 2 plus 4 is 6, so the trace of that matrix is 6. What is the trace? There's a kind of way that you can think of the trace as the derivative of the determinant, but that's nothing to do with us for this class. Much more important is the determinant. So for a 2 by 2 matrices, the determinant of A, B, C, D is just multiply the main diagonal together, AD, and subtract the product of the off diagonal, BC. So for example, the determinant of 2, 1, minus 3, 4 is 2 times 4 minus 1 times minus 3. 8 minus minus 3 is 11. Okay. Now for matrices bigger than 2 by 2, you use this method of cofactors. I'm not going to go into that there. We might do an example later on. Look at Appendix C in the book. I've also made a copy of that and put it on Blackboard. If we do anything bigger than 2 by 2 matrices, they're going to be kind of sparse matrices. There's going to be lots of zeros, so the figuring out the determinant is actually going to be okay. Now the determinant looks complicated, but it's actually a really, really important thing. So one place you see the determinant is if you try and solve a system of n linear equations. The determinant of the coefficients of those equations turns out in the solution. A fact that you might know and that you should know, and that you should take it from me, is that a matrix is invertible if and only if its determinant is non-zero. Okay, and that makes sense by what I told before, right? Because you're going to solve a system of equations, and you're only going to, if the determinant is non-zero, that means the denominator is non-zero, so that means you get your formulas for what turns out to be the solutions to your system of linear equations turns out to exist. That's an algebraic way to think of determinant. Another way to think of determinants is that it's all to do with linear independence. So if you've got a set of n-dimensional vectors, so you can put those coefficients then into an n by n matrix, and that's the set of vectors is linearly independent if and only if the determinant of that matrix is non-zero. Okay. There's also a geometric way of thinking of determinant, and that's that for a 2 by 2 matrix, you take the unit square and you can transform it by the matrix, and the determinant of the matrix gives you the area of the parallelogram which is formed by the transformed square. And the same is true for higher dimensions. So 3 by 3 matrix, you've got a cube, a unit cube. It's transformed by the matrix into I don't know what you call it, parallelepiped maybe, I don't know. It's the volume of that. And higher up, it's the n-dimensional volume of the transformed n-dimensional cube. Okay, and then if the determinant is negative, that tells you that the handedness of the system has changed. So it'll take, you know, reverse the left-handedness of the right hand. It'll take a right-handed system to a left-handed system, etc. So it's a really fundamental thing. Now, another thing that's really important, and this is probably the hardest thing, is the eigenvalues and eigenvectors. And this is, I told you before that linear algebra gives you magic fairy dust, and this is where the magic fairy dust comes from. Eigen is some German word, which is kind of mean true or of the nature of. So if you know the eigenvalues and eigenvectors, you really, really know what the problem is. So, if for a square matrix, if you have a non-zero vector u that satisfies AU equals RU, so R is some scalar, and we say R is an eigenvalue of A, and the vector U is the eigenvector of A, and the pair RU is an eigenpair of A. Those of you who've done linear algebra know that typically you use lambda instead of R, but I'm deliberately using R because we've been using R before for characteristic polynomials. Remember, we get e to the RT. This turns out to be exactly the same as that R there. So here's an example. We've got a matrix -2, 2, 1, -3. So if we multiply that by the vector 2, 1, check it, and we get -2, -1, which is, of course, -1 times our original vector. So that tells us that 2, 1 is a -1 eigenvector of that matrix. And that means -1 and the vector 2, 1 is an eigenpair for that matrix. Okay. Finally, let's have a look. Linear systems of ODEs. We can put them in matrix form, right? So we can, if we've got a linear system, we can write it as x prime equals ax plus b. Okay, so x is our vector of dependent variables. A is the coefficients of our dependent variables. We can turn that into a matrix. And B is the non-homogeneous part of the equation. And so this is going to be the convention we're going to use for the rest of the course. We're going to use a capital letter in boldface to denote square matrices and lowercase letters to denote column vectors. And so here's an example. Here we've got x double prime plus 4x prime plus 5x equals e to the 2t. Okay, that's a second order equation, non-homogeneous. Okay, we turn it into a system of first order equations by letting x1 be x and x2 be x prime. Okay, and then we have x1 prime equals x2 and x2 prime equals, well, we get the equation, we put everything on the right hand side, so we get minus 5x1 minus 4x2 plus e to the 2t. Okay, and so we can write that then as a matrix equation. We've got x prime equals that matrix 0, 1, minus 5, minus 4. Okay, so the first rows of a differential equation which you've turned into a system is always going to be it's going to be zeros, and then you're going to get a 1. That's sort of 1 off just off the main diagonal. That's time x, plus you're going to get the non-homogeneous part, which for us is e to the 2t. Okay, so the second module question, should hand to me on Wednesday, is convert x triple prime plus 4x equals 0 into a first order system, and then put that into matrix form. Okay, so we're going to conclude by looking at the double spring mass system. So this is kind of like, we're going to solve this. And we're just learning. I'm just teaching you the techniques that you need to have to be able to solve this. Okay, so remember that our system was x1 prime equals x3, x2 prime equals x4, and then x3 prime and x4 prime. Okay, so they're the second derivatives of our displacement function equals k on minus m times different combinations of x1 and x2. Okay, so to make life easier for us, we're going to let omega squared equal k on m. And we're doing this because if you remember the single spring mass system, that omega squared, we let omega squared equals k on m, and then omega turned out to be kind of like the natural frequency of that system. And it's going to turn out, giving nothing away, that here we're going to get natural frequencies which are going to be kind of multiples of omega. Okay, that's the end of the module.